Hey class, here is my little mini lecture. Since we're not going to meet this week, this is my little mini lecture on how do you take a system of equations, turn it into a matrix, and perform the row operations or Gaussian elimination on it to arrive at a solution. So I just randomly took a problem out of the book. This is one of the even problems, and I took a snapshot of it, placed it in here, and then I worked it out, and then now I'm going to go back and talk us through it. Okay, so what you're going to find out is, as you read through, if you haven't yet, that this box right here, called an augmented matrix, is exactly the same as this system of equations. Right here, it's 1x, so there's 1x. 1y, there's 1y. 2z's, there's 2z's, and it equals, this is the augmentation, is kind of the equals line. And then you have the 8. Here's the 3x minus y plus z is 0, this line right here. And then finally, here's the negative x plus 3y plus 4z is negative 4, that line right there. In the book, they call it a pivot. You always want to get a 1 in this upper left-hand corner of the matrix. We already have it as a 1, so I didn't have to do it. If it wasn't a 1, I could either say it was a 5. I could divide everything in here by 5, and then it would be a 1. Or if there was a 1 down here, I could swap those two rows and change it to make there be a 1. But once you have a 1 here, you're going to use it to annihilate these two values right here. So the first thing I'm going to do is change that. I want to get it to a 0. So I just think, using this, how would I make that spot into a 0? Well, if this was a negative 3 and I added them, then it would work. And so I then over here say, or I could do 3 of these and then subtract that. That's what I wound up doing over here, you can see. So I said, well, let's take 3 of the row 1s and then subtract it from row 2, and let's replace that with row 2. That's exactly what you would do up here if you were trying to eliminate, let's say, x's in these two equations. You would say, let's multiply this by negative 3, everything here by negative 3, and add it to this equation, and then we will get rid of it. So we're doing elimination without the variables and without all the extra stuff. So then what I've done down here is I've just 1 times 3 is 3, and 1 times 3 is 3, and 2 times 3 is 6, and 8 times 3 is 24. And then subtract, I put that there to remind me, 3 minus 3 is 0. 3 minus negative 1, you add, it's 4. 6 minus 1 is 5. 24 minus 0 is 24. Now that's going to go into row 2. So down here, if you look, that row is exactly the same row 1 is, and row 3 is exactly the same. What changed is row 2, but that's because I operated on it and I'm replacing row 2 with something else that's equivalent to it through what we call row operations, which are really just adding equations together, doing elimination like we've done our entire algebra career. So now I've got a 1 there. I want this to be a 1. So looking at this, I'm going to ask myself, well, how can I use this and make this into a 0? Well, if I just straight add them together. So you can see over here, I said, well, let's add those two together and replace row 3 with that. So I just copy this row exactly right here, copy this row exactly right here, add them all straight down. You can check. That's supposed to go into row 3, so notice here, row 1 is the same, row 2 is the same, but row 3 switches. And so I'm using the new row 3 right here into row 3. Now that I have these zeros, I want to make that a 0. This is called the lower triangle. We'll talk about upper triangular matrices and lower triangular matrices, diagonal matrices. We'll talk about all of that coming up. But we're trying to eliminate this lower triangle, and then we're going to use the upper triangle, and we're going to leave the diagonal in place. The diagonal turns out to be really important for a lot of different reasons that we'll investigate and find out. So I want to get rid of this. Well, I see if I just subtract these two rows, this minus this, so we'll put a 0 right here. And so I said, let's take row 2 and subtract it from row 3, and let's replace that into row 3, so I get a 0 right here. So copied them down, subtracted them, look at my row 3, look at it change, but the first 2 rows don't. And now I really want this to be a 1. So I can take and divide everything in this row by a constant. So if I can multiply by a constant, I can divide by a constant. So I'm going to divide everything by -1, or multiply everything by -1 if you want. And I didn't do the calculation there, but it turns a -1 into positive and a positive 20 into -20. Now I make this note here saying, okay, now this is technically enough to obtain a solution. This is actually what they call row echelon form. And so we're in row echelon form right now. And once you're in row echelon form, you can pull the solution straight out of the matrix. So how do you do that? And here's how. This last row says no x1s plus no x2s plus 1x3 equals -20. Or just x3 is -20. So I already know x3, or z if you want to. Now this row says no x1s, 4x2s plus 5x3s is 24. So 4x2s, 5x3s, or 4x2s plus 5x3, now I know is -20, is 24. That's -100. If you add it, you get 124. 124 divided by 4 gives you an answer of 31. Then the top row says x1 plus x2 plus 2x3s is 8. So I put that here. Here's x1. X2, there's the x2, and we just found that it was 31. And we have 2 x3s. Well, if you double -20, you get -40. And then if you add 40, you get 48. Subtract 31, you get 17. So I could see that if I wanted to write this, the answer is 17, comma 31, comma -20. It's a point, a single point, where those 3 planes happen to intersect. Okay, but we're not technically done there. And so, coming up here, now what I'm going to go for is I'm going to try and zero this out. You'll find, and you just have to trust me on it, or trust yourself enough to play with this and convince yourself. Notice I did a pattern where I did this one, this one, this one. Then I'm going to do this one, and then I'm going to go here and here. The reason is because if I went here and got those, or let's say I zeroed this one out, and then I went to zero this one out. Well, if this one's a 0, I'm going to have to multiply this row by something. But this is a 0. So when I multiply it by anything, this number will be not equal to 0. And so when I add it to this, it's going to replace a 0 here with something that's not 0. So I'm going to, in a sense, shoot myself in the foot over what I just did. I'm going to undo valuable work that I just accomplished. And so there kind of is a pattern to this, so that if you look here, when I do this, now I've got zeros on both sides of this. So if I use the bottom one to wipe this out, this won't fill anything in here or mess it up, and this won't mess anything up here. So I'm pretty safe there, and I can use just this to manipulate that. And in this row then, once we're down here, I can use the second row. Since it's got zeros on both sides, it won't mess with anything in here. And so I can just use this to wipe out the middle term, but these terms won't change these numbers in there at that point. So anyway, that's my little spiel on that. You just have to trust me or read in the book and see there kind of is a set way to go about eliminating all of the zeros in a matrix. And there is a right way, or a right pattern, and there is a wrong pattern. And the wrong pattern will start to fill back in zeros that you did work to zero out. So with that being said, I'm going to zero this spot right here. The way that I'm going to do it is, if this was a negative 5, I could take a negative 5 and add it to that. See, this in here being a negative 5 won't affect this, so I won't affect that first part of that row in there. And I'm just going to be able to use this to build up some work in. So you can see I said let's take row 2 minus 5 row 3s. So since I have the minus in here, it's out here kind of invisible. And so look what I've done. I just did 5 times row 3. So 5 times that is negative, well, I did negative 5 times it. So negative 5 times it, that's what's wrong. All right, so if you do negative 5 times this, it's negative 5. And negative 5 times this makes it positive 100. When you add them, this is what you get, and I'm going to replace that into this row. Now that I have that, I have this that I can use just to annihilate that, and I have this that I can use just to annihilate that, and I won't fill anything back in these by doing that. So I want this though to be a 1, so I'm going to divide everything by 4. If you do that, you get a 31 there. Now then, I'm going to wipe this out using row 2 to wipe it out. I see if I just subtract the 2, it'll work. So I take the first one and the second one, subtract the 2, fill it in here. Now I want to wipe this out, so I can use row 3, 2 of these and this. And so I take row 1 minus 2 row 3s to zero that out. And then I have it here. Now this is the final matrix, and this is what's in what we call reduced row echelon form. And since it's reduced row echelon form, you can actually see the answer in here. The answer is x3 is negative 20, x2 is 31, and x1 is 17. But the way it really comes out is this, and I apologize if you're bored by this, but this says 1x1, no x2s, no x3s is 17, so I wrote that right here. Well, that's nothing, and I don't need the 1 in there, so x1 is 17, there it is. No x1s, 1x2, no x3s is 31. Well, those don't matter, and that doesn't matter, so x2 is 31. And here, the same thing, x3 is negative 20. But look, that is exactly what we got when we back substituted out. So you can get to row echelon form and then back substitute out, or you can go all the way to reduced row echelon form and then basically read it off. X is 17, Y is 31, Z is negative 20. All right, so one other thing then is this. You're going to run into 2 other types of matrices, and they throw you for a loop the first time you see them, but you just have to trust me that you will become accustomed to it. When you get a row of all zeros, what that means is you have infinitely many solutions. If you remember, what's going on with these linear systems is if it's 2 equations, 2 unknowns, we're looking where 2 lines intersect in the plane. Well, 2 lines either don't intersect, they're parallel, they intersect at exactly 1 point, meaning they have different slopes, or they intersect everywhere, meaning they lay on top of each other. They're the same line, just a multiple of the other line or something like that. And so that's what happens here, is one of them, see it says this happens when one equation's a multiple of another. So for example, like x1 plus 2x2 plus 3x3 is 5, and then this one looks different. But really, if you hit this with 3, and this with 3, and this with 3, and this with 3, this row is really just 3 times row 1, put it into row 2, or whatever it is, wherever it shows up in the matrix, you understand. It's not really a matrix, this is the actual system. But this happens because then when you do minus 3, minus 6, minus 9, minus 15, you'll get zeros everywhere when you add them together. There's no way to use this row against this row and not zero them out, basically. If you're trying to get one of them gone, all of them will disappear. So When that's the case, we say it has a free variable. And whichever one doesn't have a leading 1. So this has a leading 1 in the x1 column. So x1's not free. This has a leading 1 in the x3 column. So x3 is not free. But there is no leading 1 in this column, in the second column. So then it's a free variable. Notice I said I called it t for time, or usually it's time. And so then reading this off, then I see here z or x3 is 2. x2, though, I don't have any way of knowing what it is. So I just go, oh, it's free. And so there it is. And then this says x1 plus 3x2s is 3. But I know x2 is t. So then I have a way of getting x1 in terms of t. And now if you give me any t, I can tell you an answer to that system. And so that, since t can be anything, there are infinitely many t's, so there are infinitely many answers. And so we did have a redundant, a multiple of itself. In the future, this doesn't have to be right now, but here is a way that we will want to write this. We will want to write this the following way: x1, x2, x3 equals, I'm going to call it 302 plus t times negative 310. And what that is this is 3 plus negative 3t, or 3 minus 3t right there. This is 0 plus 1t, or just t in the second spot. And this is 2 plus no t's, or just 2 in the third spot. And so this is a way of breaking it out into these vectors. And these vectors will play an important role in the future about basis vectors, kernel vectors, and things like that. So when you get a row of all zeros, that's a tautology. That's totally true, that no x1s plus no x2s plus no x3s is always nothing, no matter what those are. And so that's always true for every value. That's called a tautology. And that always true means you have a lot of solutions. So when you get something like this, this is, if we were in class, I would say this is bullshit. And this is completely ridiculous, because it says no x1s plus no x2s plus no x3s is 5. But nothing plus nothing plus nothing is nothing, and nothing can't add up to 5. And so my little thinky there, this is total BS, and there's no solution. So once you get a line in there that doesn't make sense, now notice if that's a 0, we're back to infinitely many solutions. And so, but if it's nonsensical, that's nature's way of telling us that it's because you're trying to find something that doesn't exist. You'll never find it, and we have a way of detecting that. So that's kind of the important stuff for this week that you're supposed to get out of it. This is kind of the way I want to see it if we were going to do work. I like these little boxes here where you can tell somebody a series of steps. And if we all know that R1 is row 1 and R2 is row 2, and the big numbers out front means to multiply them, and that means to store. Incidentally, if you wanted to swap 2 rows, so when that would occur is sometimes you have something like this. So you have like 0, 3, 2, 4, 1, 4, 3, 9, 0, 2, 6, 7. The thing is, I might, in my very first step, say, well, I just want to take row 1 and swap it with row 2. And what that would do is then I'd have 1, 4, 3, 9 up top, and then 0, 3, 2, 4 there, and 0, 267 right there. And now you see I have my 1 up in that top corner. I already have the 1s down there, and all it took was a row swap for that to happen. So the double-sided arrow means back and forth, but the single arrow just kind of means store, to store it into row 2. Do that operation and store that into that row in the matrix. So I hope that's helpful. Like I said, this is one of the one other thing. While you're here, hopefully you made it to the end and everything. Check this out very, very closely. We do have 2 books, and this is what's going to happen. Let me get back to both of them here. The first course in linear algebra is kind of a basic course. It has a very good exposition. It's very broke down, very elaborated. He tries to do a lot of steps and things like that in there. Incidentally, when I looked through here and got as far as I wanted you to read, I didn't see any problems. Later on in the book, after all of this, he finally gets to some problems at the end and here. And these are more like the ones that I would want you to do. And if you look there, so anyway, those are more along that lines. But that's the first course in linear algebra. The other book is Linear Algebra with Applications. And in your class, let's go your class here. Come on. So the AFC is a first course. So you can see I wanted you to read in there. And then in the linear algebra with applications, that's that LAWA, L-A-W-A book. I wanted you to do the homework from there. So if you look, this is the LAWA book, Linear Algebra with Applications. So there's the L-A-W-A. And then in this book, you're going to do right here. And these are where the problems are. And so these already look like they're the systems, that type of stuff. And so, but we will move back and forth. And so, anyway, just don't be confused. I'm going to assign these problems actually next week. So if you want to start doing some of these are like the big matricy stuff, and we will do that. But for this week, it was more just remind yourself about solving systems that you either get no solution, exactly one solution, or infinitely many solutions. Get up to date on the jargon, like when there's at least a solution or infinitely many solutions, it's called a consistent system. When there's no solution, it's called inconsistent, and all of that stuff. So just kind of welcome, and we're just kind of easing into it, but get a feel for the books, and I'll be seeing you soon. All right, take care. Bye-bye.